In this video, what we're going to do is we're going to cover a linear program that is related to the workshop example we had covered in a previous video. This particular linear program is what we're going to end up seeing is called the dual of the workshop example. So what I have kind of up on the screen right now is the description of the decision-making environment of the linear program we're going to be focusing on. So basically there's this company called Takeover Experts, and it's in direct competition with the Lego Workshop. And what Takeover Experts wants to do is it wants to buy up all of the workshop's resources and essentially take it over. So the first paragraph kind of is a description of the Lego Workshop problem we had done previously, and if you look on the right-hand side of the screen, we have the linear program that we came up with the Lego Workshop. So just kind of as a reminder, Lego Workshop builds teas. They sell for $3 and require 2 small bricks and 1 big brick. Cakes sell for $2 and require 1 small brick and 1 big brick. And then eyes sell for $4 and require 1 small brick and 2 big bricks. Now, what Takeover Experts is going to do is they're going to essentially offer a contract to the Lego Workshop in order to take the Lego Workshop over. In particular, what Takeover Experts is going to do is it's going to offer a price per resource for each small brick, each big brick, and each unit of demand for the Lego T. Now, what the Takeover wants to do is obviously the Takeover company, obviously they don't want to spend a lot of money. So they want to essentially minimize cost in taking over the Lego Workshop. However, they also want to ensure that the takeover is successful, so they need to make the deal appealing to Lego Workshop. So what this means is if I look at essentially the prices that the Takeover company is offering the Lego Workshop, I shouldn't be able to make more money by actually producing one of the products that the Lego Workshop produces. So what we'll see is we're going to have to capture that particular aspect of this decision-making environment as a constraint in the linear programming representation of the Takeover problem. So what we're going to do for now is we're going to temporarily kind of drop down the Lego Workshop example and start working with the Takeover linear program. So what we'll do initially, kind of like we always do, is we'll start defining the variables in the Takeover problem. And really what our decision-making problem for the Takeover company is to determine what the contract is going to look like that they're going to offer to the Lego Workshop. So the decisions are kind of spelled out in the first sentence describing the Takeover problem. In particular, what we are deciding is how much are we going to price each small brick, how much are we going to price each big brick, and how much are we going to price each T. So that price is what we're going to offer the Lego Workshop for a small brick, for a big brick, and for a Lego T, a unit of the Lego T demand. So what we're going to do is we're going to define Y1 to be the price paid for each small brick, and what's key is that this price is per small brick, and then we'll have Y2 similarly be the price paid for each big brick, and then Y3 is going to be the price paid for each unit of T demand signed over to the Takeover Experts. So these are the decision variables, and we want to kind of now express, well, what is the objective of Takeover Experts in terms of this decision-making environment? And like I said before, they want to minimize their costs in the takeover. So we can kind of start viewing, well, how much the cost, start breaking it down by each of the resources they're buying up. There are 200 small bricks and 200 big bricks, and then 40 units of T demand. So in kind of looking at this, we want to minimize our costs, which we can express mathematically as 200y1 plus 200y2 plus 40y3. So what we're looking at is, or what we're defining in terms of the objective is, for each resource, the number of resources that we're buying up from the workshop times the price we're paying per resource. So this 200, for example, 200y1 is the total amount that we have to pay for the small bricks. 200y2 is the total amount we have to pay for the big bricks, and then 40y3 is the total amount we have to pay for the T demand. So we have our objective, we have our decision variables, we can start thinking about, well, what does the constraints of this problem look like? And the main constraint is, for each product that the workshop offers, we need to have that the workshop is better off signing over resources to Takeover experts than it would be selling that product on its own. So what we're going to look at, or let's first focus on the T resource, or sorry, not T resource, but T product. And we can sell them for $3. And then we need to compare this. We were essentially comparing it to the price, the total price paid for resources required to kind of quote unquote sell a T. So what this kind of means, and kind of what I've written out here, is in order to sell one of the T's, we need to use 2 small bricks, we need to use 1 big brick, and we use up 1 unit of the T demand. So by using the resources, by the 2 small bricks, the 1 big brick, the 1 unit of T demand, we receive $3. The alternative is we can sign over those resources to the Takeover experts. And since Takeover experts wants the deal to go through, they want to make sure that the prices they've selected for those resources, the 2 small bricks, 1 big brick, 1 unit of T demand, exceed, or at least as large as $3. So what this means is we're going to have a constraint that compares the price paid for the resources required to pay the T, or build the T, and we're going to compare it to the revenue that the workshop can receive from actually selling the T. So what we'll have is we'll have a constraint of 2y1 plus y2 plus y3. If I look at what we're adding up, is for the T, I need 2 small bricks. And I can look at, for those 2 small bricks, how much money am I getting in the Takeover problem based on the prices that we've selected for the small bricks. Then I can add this to the price I receive, or the money I receive from the Takeover, which is y2, for the big brick that's used for the T product. And then also I can look at the revenue that I receive, or the price I receive from the Takeover experts for the T demand. So this would be the total amount of money I receive from Takeover, the workshop receives from Takeover experts, assuming I use the resources required to build a T, and instead of building the T, I sign those resources over to the Takeover experts. So we're going to have a constraint that says 2y1 plus y2 plus y3 is greater than or equal to 3, which is the amount of money I can make from selling the T's, selling a T. So we're going to have a similar constraint for both the cakes and the eyes. So for the cakes, I need 1 small brick and 1 big brick. So what this means, if I take the 1 small brick and 1 big brick, instead of building the cake, I sell them to Takeover experts, I'm going to receive a total amount of y1 plus y2. And then that needs to be greater or equal to the amount that I can make from just building the cake with those resources. So that has to be greater or equal to 2. And then we're going to have a similar constraint. So I'm going to just kind of list this. This is the t constraint. And then down here, the second one is the cake constraint. And then finally, we also have a third constraint for the eyes. And for the eyes, I need 1 small brick and 2 big bricks. So the amount of money I get from signing those resources over to the takeover company is y1 plus y2, and then that needs to be greater than or equal to 4. And these are the eyes constraint. And then we're going to also just have the non-negativity constraints, so y1, y2, and y3 are greater than or equal to 0. So I'm just going to kind of clean up the takeover LP, and if I look, essentially this is a linear program that we're facing with the takeover example. And now I'm going to compare this or bring back up the Lego workshop example. And just kind of comparing these two, there are some similarities. I mean, if we look at the listed constraints, in particular small brick, big brick, and T upper bound constraint in the Lego workshop problem, there are variables over in the takeover problem that are concerned with small bricks, big bricks, and T demand. And then if I think about the decision variables in the Lego workshop, I have decision variables associated with T's, cakes, and I's. And then in the takeover problem, I have constraints associated with T's, cakes, and I's. So there's kind of this nice synergy between the Lego workshop problem or linear program and the takeover linear program. And what I want to do is I want to highlight the kind of comparisons between these, and I think that's a little bit easier done using colors to show you where things are. So I'm going to bring up a document that just kind of lists and condenses the two linear programs together. So what we have over here and kind of what we have is a comparison of the workshop linear program and the takeover linear program. And from a technical perspective, the workshop and the takeover are what are called a primal dual pair of linear programs. So we're going to kind of go through what makes the takeover problem the dual of the workshop problem. So the first thing is that with any kind of primal dual pair is that the objective functions are quote-unquote opposites. So we're maximizing profits in the workshop example, we're minimizing costs in the takeover example. So kind of that's a pretty simple kind of relationship. The next relationship we want to kind of highlight is that, like I said before, each variable in the primal problem has a constraint over in the dual problem. So the different variables are highlighted in different colors here, but let's focus on the T decision variable, so x1. Well, if I look at x1, its leading coefficients in the three constraints become the leading coefficients of the associated dual constraint. So remember, I kind of mentioned before that y1, y2, y3 correspond to each of the constraints in the workshop problem. So we're multiplying y1 by the leading coefficient of x1 in the x1 constraint. And then we do the same thing with y2 and y3. And what becomes interesting is the right-hand side of the takeover constraint is the objective function coefficient of the x1 variable. And this relationship holds also for the cake production decision variable and the and the I production decision variable. So the cake is highlighted in the blue, and the I is highlighted in this purple color, or light purple color. And then the next kind of comparison, so again, so with this, I mean, every variable has an associated dual constraint. So, and then the dual constraint takes the coefficients in the different constraints for that in the different constraints of the primal problem for that variable. And like I said before, there's also kind of this relationship between dual variables and constraints in the primal problem. So each constraint in the primal problem maps to a variable in the dual problem. So as kind of a highlight, we'll focus on the small bricks for now. The small bricks constraint becomes essentially a variable in the dual problem. And what we see is that the leading coefficients of the different variables in the primal problem end up being the leading coefficients of the column associated with the dual variable associated with this primal constraint. And like we saw in going from the primal to the dual for the variables, for the variables in the primal problem, what becomes interesting is that the right-hand side of the constraint in the primal problem becomes the objective function coefficient of the dual variable associated with that constraint. So we saw the same thing where the objective function coefficient of a variable in the primal problem becomes the right-hand side of its associated constraint. So, and you could see the same highlights for the big bricks and the t-limit variables as well. I want to emphasize one kind of interesting aspect is since every primal variable has a dual constraint and every primal constraint has a dual variable, we can start and try and take quote unquote take the dual of the dual, and we end up with the original primal problem. So these primal and dual problems are pairs. So every primal has a unique dual, every dual has a unique primal, so the kind of labeling of primal dual is kind of not arbitrary, but it doesn't matter which one you call a primal, which one you call the dual. So what I want to do kind of just to wrap up this is to introduce a couple concepts of why the dual problem to a linear program is a powerful concept. So what we'll do is we'll bring up the Takeover LP in the Lego workshop. And what I've listed in the Lego workshop LP is the optimal solution to the problem. So the optimal solution was to set x1 equal to 40, x2 equals 0, x3 is equal to 80, and we end up with a total profit of 440. And what I want to kind of start thinking about and figuring out is, how much money is it going to take the Takeover company to take over the Lego workshop? If the Lego workshop can already make $440 on its own, it's kind of this nice idea that, well, by the way we've designed the constraints in the Takeover problem, it should cost the Takeover experts at least $440 to take over the workshop, because the workshop can make $440 by not signing any of the resource over to the Takeover LP. So what we kind of want to establish is we want to look at kind of a comparison between implementing these production levels and selling the resources over to the Takeover experts. So right now, let's focus on one production level. We're going to focus on the T's. So if I focus on the T's, then I know I am currently making 40 T's and I get $3. So, basically the objective is 3x1, which is currently 3 times 40. And now I know that each of my resources, each T requires 2 small bricks, 1 big brick, 1 unit of T demand. So what I could do instead of selling 40 T's, I can sell the resources required to produce 40 T's over to the takeover company. So what I know right now by the t constraint in the takeover example, that this has to be 3 times 40 has to be less than or equal to 2y1 plus y2 plus y3 times the 40 production level, right? That's simply just plugging in what this constraint is comparing to the 3 over here. So what this means is that we are better off selling the resources to build T's over to the takeover company. So, and I can do the same thing for x2 and do the same thing for x3. So what this tells us is if I kind of sum all of these, so 3x1 plus 2x2 plus 4x3, this has to be less than or equal to 2y1 plus y2 plus y3, x1 plus y1, y2, x2 plus the y1 plus 2y2, x3. So all we're doing is plugging in these comparisons to the objective. So what this is a concept of weak duality. Any solution, any x values to the primal problem have an objective less than or equal to any values for y in the dual problem. So what this kind of means is that I know any feasible solution to the workshop example has an objective function less than or equal to any feasible solution to the dual problem. What is nice about this is that it gives us a natural lower bound and upper bound on the objective function of the tool to problem. So I know that the workshop problem, if I have a optimal profit level of 440, the takeover is going to require at least $440. And we can use this in kind of comparing these solutions. So we know that the optimal solution x1 equal to 40, x2 equal to 0, x3 equal to 80 results in total profits of 440. We can kind of look at feasible dual solutions and see if they have an objective function of 440 or not. So let's look at a solution where y1 is equal to 0, y1 is equal to 0, y2 is equal to 2, and y3 is equal to 1. So I'm just going to kind of bring this over to the takeover problem. Now one thing is we can start making sure that the constraints are satisfied. This satisfies the t constraint because we're adding up y2 and y3 for a total of 3. For the k constraint, y2 is equal to 2 is greater than or equal to 2, so that's good. And then we see y2, 2 for the i's constraint, 2y2 is 4, which is greater than or equal to 4. So this is dual feasible. And more importantly, if I look at the objective, it has a cost of $440, right? So we're dual feasible. We know that we cannot take over the problem for any less than the workshop's maximum profits. So this is optimal to the dual problem since it has an objective equal to the optimal solution to the primal problem. So using weak duality gives us that this solution has to be dual optimal. So we have this concept of not only weak duality but strong duality is they're always, or not always, but the optimal objectives of the primal and dual problem are equal, assuming they are bounded. So there are some special cases where if your dual problem is infeasible, so it doesn't have feasible solutions, you can drive the objective of the primal problem arbitrarily large. But if both primal problem, dual problem are feasible, then the optimal objectives are equal. And there's kind of this nice connection between using the simplex method to solve the Lego workshop example and the dual variables of the takeover LP. But that's kind of another discussion. So, all right, that kind of concludes this particular video.